we're going to learn their interesting probability distribution. It's called Poisson. So it's a French name. Probability distribution. General idea about the probability distribution, and we learned binomial distribution, and this is the, and let's do a quick review about a probability distribution. We have an x, and we have the probability of x, and that's the first requirement. Second requirement, all the probabilities add up to 1. The sum of all the probability is 1. Number 3, third requirement, every probability, every single value should be between 0 and 0. Could be 1, could be 0, but nothing more. Nothing negative, nothing more than 1. But for the binomial distribution, there's 4 requirements. There's an n, so which is a of trials, and each trial is independent. The third one is a probability of two outcomes by means, right? And the last one, the probability of success stays the same for each one. What is a probability distribution? Again, this distribution is also a discrete probability. See that a binomial is discrete, right? Because that x could be 0 to 1 and the 2 and 3 and all the way to n. It is a discrete. Poisson is also the same. They're different. What does that mean? Is a Poisson distribution applies to occurrences, some event, and over a specific interval. The random variable x is the number of occurrences of the event in an interval. This interval could be in a year, a mile, a distance, right? A mile. Could be in volume, some volume. I see. I don't know. Cubic meter. Okay, whatever. It's just one interval. It's just in an interval. So how many number of occurrences of this event in an interval? So that's x, and the probability of that, the Poisson distribution. The probability of that is this. It's very hard to remember. It's mu to the x, e to negative mu, factorial. It's scary, isn't it? What is e? E is 2.71828. It's just almost. It's because it has a lot of numbers. It's a rational number. So that's e. Now you look at this formula. If you know mu, so you know here, and you're looking for the probability of x, and then e is a constant, it's a number. All right, so it seems like the only thing you need to know is mu. What is mu? Mu is the mean number of occurrences of the event in an interval. It's the same thing as here. Okay, I just don't want to copy that. Alright, so we know the average number, and we want to know what is the chance that any other value comes with, what's the probability. So again, there are 4 requirements again, okay? So number 1, 4 requirements. Same thing. Number 1, interval. We always talk in certain interval. Okay. Number 2, very random. Every single occurrence is random. Number 3, independent. Number 4, the occurrences are uniformly, what does that mean? Distributed. Whoa, it doesn't make any sense right now, right? Okay, now let me give you an example. I just say in California, okay, averagely like there are 50 earthquakes. In a year. So mu is 50. A year is a time interval. See, it's an interval, and all the earthquakes occurred randomly, and then they're all independent of each other. We just assume they're independent, okay? The independent means occurrences must be independent of each other, and they're uniformly distributed. That means, okay, that means the this earthquake in a year time period from January the 1st to December the 31st, any day they have an equal chance to have earthquake. That means uniformly distributed. If that's the case, then the probability of, let's see, what is the probability that averagely 50 in a year? What is the probability that this year we have 100? That is x, and that's the probability of x, okay? And all the probabilities add up to 1. We don't know yet, but I tell you it is. And the probabilities should be between 0 and 1. All right, can we find it? Yeah, we can find it by using the formula. Do you remember the formula? It's mu to the x, e to negative mu, and then the x factorial. Okay, so that's p of x. All right, now in our case, we're looking for p of 100, and the mu is 50. So that would be mu is 50 to the power of 100, and the e to negative mu, which is negative 50, over 100 x factorial, which is 100 factorial down there. Okay. I don't think you can do anything by hand. You have to use your calculator. Let me show you how to use the calculator here. All right, so 50 to the power of 100 times, and the e to negative power, so it's see what I'm doing? Okay, so 50 negative and e to this power. Is it the order? You do 50, and then you do this a plus minus, you change that to be negative 50, and then you click this e to the x, so that goes to the top, and then we divide it by 100 factorial equal to, oh my god, it's tiny, it's a very, very small number, so that chance is 1.6.3 times 10 negative power. So the chance you have is 100 earthquakes in that particular year. It's almost zero. Okay. Yeah. If it's a 50, then what is the chance that we have? What is the that we get a 52 exactly 50? Right, that would be, bring this down and put everything to show that on the same screen. So that would be mu is a 50, the power is a 52, that's x, and here's e to negative of 50, and here's a 52 factorial. Okay, so let's do that. I'm showing you how to do the calculator. 50. So 50 to the power of 2. Okay, multiply by 50 negative to that power divided by 52 factorial equal 5%, 3%, is 0.0531 because that's 531. So it's about 5.31%. All right. So that means in California have 50 earthquakes in a year. What is the probability that particular year they get exactly 52 earthquakes? The chance is 5.31. Okay, 5%. Interesting. Okay. After we get the probability distribution, we get the formula how to calculate probability distribution. You know what we're going to do next, right? Next, mu and the formula. Mu is just given, all right, and sigma is square root of. Now let's use again. We use the earthquake example. Mu is 50. Sigma is 50. So 50 square root, which is 0.1. I just okay. So then we can find mean. What it this mean? We have sigma, so we can have mu minus 2 sigma, and we will have mu plus 2 sigma, right? So 50 minus 2 times 7.7, and 50 plus twice of 7.1, so that's a 64.1, and this one is so it's a 35.8. Okay, for any given year, if the number of earthquakes is greater than 64.1 or less than 35.8, are considered as significant. So this side is significantly high and this side is significantly low. Any number between these two are not significant, which means we're not surprised, or most of the data should be between these two numbers. That's what it means. All right, now other than this, let's give you another example. This is the earthquake. So you probably see that in most of the time we talk about the disasters, right? Hurricane. There have been 652 Atlantic hurricanes during 118 years. Okay? All right. We assume that the Poisson distribution is a suitable model. So we're going to use the Poisson distribution. Can you find a mean number of hurricanes per year? So that's how many hurricanes in this many years. So therefore, the mu should be 652 divided by 118. The answer is 5.5. Okay, hurricanes in a year. That's a time period, huh? All right. Now, can you find this? That's the mean. And can you find what is the probability that in a randomly selected year, what is the probability that there are exactly 6 hurricanes? Can you find it? P of x. Do you remember that? Do you remember the formula? Mu to the x. Mu is this. So 5.5 to the 6. And then e to negative mu. So negative 5.5 divided by 6 factorial. So the answer is, do you want me to, I guess it's, okay, so let's do that. One more time, okay? So 5.5 to the power of 6 multiplied by 5.5 negative e to that power divided by 6 factorial equals, so the chance is 1571. So that's a chance. So the probability of getting exactly the 6 hurricanes in a year is 1571. Okay. The next question. There are exactly 16 years out of this 118. So 16 years. 16 years with the 6 hurricanes. What do you think? I would think if it's the chance is this. So let me use 118 times 0.1571, and then I get what I get I multiply by that, I get 18.5. So for 118 years, this is the probability that they're going to have exactly 6 hurricanes. So that should be 18.5 years have 18.5 years with exactly 6 Atlantic hurricanes, and we have 16. It's not too far away, so we think, yeah, that was okay. The Poisson model appears to work quite well in this situation. Okay, so that is the something, and then we have to know a little bit more about Poisson distribution. Is the Poisson distribution sometimes used to approximate the binomial probability distribution. They're different, okay? Okay, when you see Poisson, you would think if we talk about a Poisson distribution, that x is the number of occurrences of the event in an interval. So that could be 0, could be 1, could be 2, 3, 4, 5. It could be 1 million. Even the chance is tiny, 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 but it's possible. I don't know. It's possible to have 1 million earthquakes. All right. But anyway, so that x is very different than the binomial. Binomial, the x could be just 0 and 1, 2, 3, 4, all the way to n. But in Poisson distribution, that x could be 0, 1, 2, 3, 4, all the way to a huge number. However, we can still, when n is really, really large, and the p is very, very small. So when n is large, and the p is small. Okay, literally we have to say when n, how large? 100 or more. How small the p is? np less than or equal to 10. That's, you have a really large n and you have a tiny small p. If this is the situation, if both the requirements are satisfied, then you can use Poisson as an approximation to the binomial. What does that mean? Okay, then for the mean for Poisson is the mean. We know binomial, but for Poisson we know that we need to know the mean. That will be just np, and it has to be less than or equal to 10. What does that mean? How do we use this? What is the concept here? That means when you work on the experiment and the chances is small, and you work on that again, chances small, many times, then the Poisson distribution and the binomial distribution, they're very close to each other. Is that right? Let's see. Okay, we're going to use another example just to talk about this. All right, in main pick 4 game, you pay 50 cents to select a sequence of a 4-digit. So you're going to spend 0.5 to play pick 4. Okay? And you do this every day. You do this once a day. Now, what is n? How many times you do this? 365, right? And what is the chance of winning? 1, 2, 3, 4. You have 10 choices here. 0 to 10, 0 to 9, 0 to 9, 0 to 9, 0 to 9. So the chance is 1 over 1,000. 1, 2, 3, 4, 4, 10,000. Do you agree? Chances are small, but you repeat this a lot of times, right? So you have is n greater than or equal to 100? Yes. Your NP equals 365 times 1 over 10,000. The chance is the NP is 0.0365. Is this less than 10? Yes. Okay. So that means these two probabilities are pretty much the same or very, very close. For binomial probability distribution, if it's a binomial, let me ask you, what is the probability that you're going to win at least once? What is the probability that x is greater than or equal to 1? Isn't it? And that would be 1 minus the probability of 0. That means you keep losing. You're not winning anything for the whole year. And then 1 minus that, which means you're going to win, either once or twice or whatever. Binomial, I would ask you to find the probability of 0. So P of 0 is, do you remember the formula? Let me write it here, which is n factorial over n minus x factorial p to the x q to n minus x, right? Okay, so in this case our x is n is 365 and p is 0.0001. So n factorial is 365 factorial minus x is 0. So that's 365 minus 0 and 0. 0 factorial by definition is just 1. So the whole thing here is just 1. And the p is 0.001 to the power of 0. And then 0.9999 to the power of 365 minus 0, which is 365. So this is 1, this is 1. Then we only need to do 0.9999 to the power of 365. So the answer is 0.9642. That means you have a really, really big chance, 96.42% of the chance that you're not winning anything for the whole year. All right? So that's what you do if you use binomial. What about the Poisson distribution? For Poisson distribution, let's find out what is a p of 0. And if you remember, I don't know, the p of x, if you can remember this formula, which is mu to the x, e to negative mu, and the x factorial. So we have do we have a mu? Mu, we did, right? That, because when we checked, and then we have this mu equals, when we check this, mu is just np, so mu is 0.0365. And what is x? 0. And then times e to negative 0.0365, negative mu, and over x factorial is a 0 factorial. So here's a 1, here's 1. We don't need to worry about that. We only need to calculate e to that power. So 0.0365 0.0365 e to that power equals 0.9642. Hey, 415, so 42. Now, this is by Poisson. This is binomial. Very close, isn't it? And of course, if you want to calculate something else, if you want to find what is the probability that you're going to win just once, which will be P of 1, here will be P of 1, and of course you can just plug in the formula and then to get that. But Poisson distribution is a pretty frequently used in like earthquake, hurricane, and those type of situations. But this is a good example. So we finished probability distribution concept. We finished the binomial probability distribution, and now we finished the Poisson probability distribution. You have learned a lot. Congratulations.